it says let f be function defined above, where c and d are constants. F is differentiable at x equals 2. What is the value of c plus d? So we know that x is differentiable.
Not x, but f.
Yeah, sorry. F is differentiable at x equals 2. So should we take the derivative of f when x is equal to 2?
So what I would do is, when I read this, okay, so I have the habit of reading the word f is differentiable and not really worrying about it, because most of the time it doesn't make much difference. However, in this problem, f being differentiable at x equal 2 is the only clue. There is no other clue given. That's it. So it must have some significance in this case. The thing you should flashcard remember is f is only differentiable at x equal 2 if f is first continuous at x equal 2. So that must be a flashcard memory. Good to there. So that's what I wrote down. And then from there I remembered that, oh, f is continuous at x equal 2 only if the following is also true. That right there.
Yeah.
So I wrote that I would write that on my paper. Another common cause of a lower test score than you anticipate is not writing enough. It's trying to do too much in your head. So.
Are you doing limits because you want to forget the constant?
No. Oh yeah, thank you. I misunderstood. Exactly. When it said find A and C and D, I'm like, oh, forget that. I'm not paying attention to that. I'm going to pay attention to some other clues. So the other clue I'm paying attention to is for f to be continuous at x equal 2, this has to be valid. And I don't try to solve, I'm not as good as Megan at trying to do the whole thing in my head and then get it on paper. I just write this down and I'm like, okay, well, I have that written down. How might that help? So what would you do now?
You would be find what, so we know that the limit of f of 2, well, we know that the limit of, as x approaches 2 minus, as x approaches 2 minus, the limit of f of x is equal to f of 2 as the same. So
just don't study in between.
that means that the limit of f, the limit of f of x as x approaches 2 is a value. So should we wait? So if f2 plus, then we can plug in. Then we can use almost 2 for the bottom function, where x is greater than 2. Correct?
You lose a little more than 2 for the bottom function.
Yeah. Yeah, sorry. So you would use 2 plus for the x is greater than 2 function, which would give you just over 4 minus c just over 2.
So what you're doing is smart. You're saying, okay, let's go find it. If these two things are supposed to be equal, let's find them. Because that's the whole idea of ignoring the c and the d, is to do something else. So I say, to find this limit, I must use this equation. And I must think of x as being slightly more than 2. So 2 squared is
4.
4. So I get really close to 4 minus 2 times c. So this is what I get. The limit as x approaches 2 from the right of f is going to be 4 minus 2c. And you should practice writing out the limit statements, because on the written section you're going to have to. So if you learn to do it now, you won't have so much trouble reminding yourself to do it later. So
So then do you put 2c plus d equal to 4 minus 2c or no?
And why?
Because
Never do anything unless you know the reason.
it's continuous, so they have to be the same.
Right, that's the reason. So just don't ever do anything unless you know the reason. Sometimes the reason is just a rule, but you must at least know that it's a rule.
Mm-hmm.
So because the two limits must be the same, these two must be equal. So that's what I wrote. Now what?
Algebra.
We'd like to do algebra, but we are in a spot that's going to be a dead end. Who knows why this is a dead end?
Oh, because there's no c.
When you have an equation with two unknowns, it's what Chris was doing over here. How many unknowns are there in this equation? 2. You can't find the other unknown unless you know one of them. So the same is true here. That's an equation, but I mean, I could try and solve. I could like move the 2c over here. That would give me what? 4c plus d equals 4. It's still one equation, two unknowns.
Well, then,
There's no way to solve one. That's why they said solve for c plus d. They don't allow you to back solve it. Like, they're smart. They're like, oh, well, students will just think they can plug in numbers, but if we make it c plus d, they can't plug in numbers.
Then how do you do it?
could you,
So are you okay? Are you okay that we're stuck here? So now you have to remember, differentiable also means this. F won't have a corner and F won't have a vertical tangent. And F prime must fit this equation. So this is your flashcard right here. This is all flashcard memory. If F is going to be differentiable at x equal 2, first of all, F must be continuous, which means this must be true. Second of all, F can't have a corner or vertical tangent, which means this must be true. So what do I do now?
so,
You find the derivative?
So we find the derivative. Because remember, this is a formula for F, but it's nothing special. This just says F, whatever F happens to look like, if I can get the word to work, F's just split at x equal 2. So this is like x equal 2. That's where F kind of splits. And there's one formula over here for all the points on F, and a different formula over here for all the points on F. It's nothing special, that's all it is. So how do you take the derivative of F?
which, could you take the derivative of each individual limit formula?
Why does that make sense?
Because you know that they're all equal to each other, so finding the derivative of a common factor for both of them would help you find what the third one is. Like, if you, because if you take the derivative of the limit as x approaches 2 plus.
Slow down, slow down, slow down. So what do you want to do first? Like, don't do too much.
Take the derivative of the limit as x approaches 2 plus.
Take the derivative of the limit.
Yeah.
Well, I don't understand why we're taking the derivative of the limit.
Because it's equal to.
No, oh, you're saying it wrong. This is the limit of the derivative.
Oh, yeah.
Yeah, we do want to find the limit of the derivative. But
Yeah.
how do we find the limit of the derivative?
Well, we know the formula for the limit of the regular f, right? So couldn't we take?
So let me say back to you why that's wrong.
Okay.
So this is the value of the limit of f as x approaches 2 minus. Okay, that's not the derivative or anything. That's just that limit. This doesn't say take the derivative of this.
Okay.
It says take the derivative of f.
Okay, so then we would take the derivative of f when it is, you would take the derivative of the.
Let's pause for a minute. You're doing really well, but we're kind of getting lost in steps. We're losing the reason. And you're all just either just hoping to make sense of it at some point, but you've got to keep track of the reasons. It really relates to the discussion we had over here a minute ago. What is the purpose of this? Okay, every problem just keeps going back to the same thing. What is the purpose of this?
Find all of the x and y's for
Find all the x and y's on F. If you take a derivative of a formula that is used to find all the x's and y's of some curve, what will the new formula be?
how to find all the slopes.
How to find all the slopes. We need that formula because we need to make sure there's not a corner or vertical tangent. What indicates a corner on F?
Sudden change in slope.
In slope. That's why we need a formula for the slope, to make sure we do not have a sudden change in the slope at x equal 2. Because the whole problem says f is differentiable at x equal 2, which means f must be continuous at x equal 2. We've already verified that.
Yeah.
F must also not have a sudden change in slope at x equal 2. So what do we need to verify that f does not have a sudden change in slope at x equal 2?
Check the positive limit.
If we're using this formula, what are we always checking?
Oh, the bottom one.
If we're using this formula, what are we checking?
Checking the points.
We're just finding points.
Oh, okay.
We're not finding slopes. So we used this formula first because we've got to make sure that we find a point and the one that's really, really close to it is still really, really close to it. Because if it isn't really, 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 really close, the function will not be continuous. That's why we first started working with the points. But now we've got to make sure that the slope does not change suddenly or the slope is vertical.
Yeah.
So then, do you take the derivative of both the equations of f?
So your thinking is better now. So why do we need to take the derivative of this and this?
Because you need to find the slopes to make sure that they're the same, so that there's no change.
Right. Stay with me for a minute. Somebody answer this. What's the purpose of this little thing here? What's the purpose of that? Matthew?
Find all the points of 2 and 4 on the curve.
Good. This is how I find all the xy pairs of f for all x's that are less than or equal to 2. So if I want to find the slopes of all those points, I have to take the derivative of that formula. Like, there's a whole bunch of calculus that is really, really simple if you understand the fundamentals. The reason most people struggle is because they never understood the fundamentals. Once you get the fundamental idea, you suddenly start going, whoa, this connects to this, and this connects to this, and it all fits together, and it's not like we're learning 20 different things, we're learning like 5. They just all connect. It's just like the discussion we had over here. So we want the derivative of f, which means we want the derivative of each piece of f, because we want to know, do the slopes of f change suddenly? Questions, comments, more discussion? So what's the derivative of f? Let's go to this page. I have a little bit of helper here. So what's the derivative of f?
C and D are both constants.
Yeah, C and D are constants. This is like looking at 5x plus 10.
So it's just C.
Just C. So f prime is simply C for all x values that are less than 2.
How did you get C?
So, are you feeling really comfortable that this is my formula for finding all the xy pairs on F for values of x that are like negative infinity to 2.
Oh, we'll find out.
So I need the derivative of this to find the slopes of f. C is a number, 6. So this is like 6x plus 5. So you tell me, what's the derivative of 6x plus 5?
So you just take out the C.
Does that make sense?
Yeah.
That's good work. Very good to hear? So now what?
Now we should find the derivative of the
Other portion of f.
Okay. Isn't it different though?
What's that?
Isn't it different?
What's the derivative of the other half of that?
2x minus C.
Minus c. Because there's one formula for finding the slopes on one half of f, and a different formula for finding the slopes on the other half.
Okay.
Because there were different formulas for finding the points.
Oh, so the limit has to be the same, not the equations, right?
Right. Because we're just trying to see what's happening at x equal 2.
Okay.
We're not saying the slope is always the same. We're saying, is the slope the same at x equal 2?
Okay. Because
this-
it says differential.
Differentiable means I want to make sure, see if f has a corner, if f does this, can you find the slope right there?
No.
No. How do you determine whether or not f does this?
By finding the slopes on either side of it.
On either side of 2, like really close. That's why we're doing this. Right there. This, okay, again, don't get lost in the steps. This simply means the slope of f really close to 2. And that's what this means. The slope of f really close to 2. This one means the slope of f at 2.
So now we do algebra, because C
We have just
equals 4 minus C.
Right, because the slope on one side of the possible corner,
Should.
we want, it tells us differentiable, so they have to be the same.
C
Okay.
is equal to 2.
So we did algebra, C is 2. Questions, comments, discussion?
Oh, that's just C.
And then we,
So question for all of you, why did I leave off the equal sign here?
Where?
Right there. There's an equal sign there.
Is it because we know? Is it because we're checking to see if the 2 is differentiable? Like,
It's the whole thing. When you have a piecewise function, when you take the derivative, you should not assume that that piecewise function has a slope at the junction. It won't necessarily. If the
If it has
piecewise
a
function has a
constant.
corner, you cannot put an equal sign there. So I teach you to not put the equal sign until you're sure.
yeah.
Now, in this problem, they told you the function was differentiable.
So
We're
we're
checking.
So we know, but we're going to force it to be. We're going to pick C and D so that it is.
So, but if it did have, if it didn't say it was differentiable, it could have a corner.
Correct.
Like just, okay.
Yeah, if it didn't declare it to be differentiable, I do not want to put an equal sign there.
Because you don't.
I don't know. If I put an equal, then I'm saying I can find the slope at 2. But if there's a corner, I can't necessarily.
So if the problem said if f is continuous at x equals 2, would it be the exact same thing, or no?
So f being continuous at x equal 2 is talking about points, not slopes. It's saying right at 2 is there a point. Like that's what this means. Right at x equal 2 is there a point.
Yeah.
Then also, just left of x equal 2, is there another point that is infinitesimally close? So we pretend it looks like that, even though it doesn't, but pretend. Just a little bit right of x equal 2. Is there another point that is infinitesimally close? That's what this is saying. This is saying the y-coordinate just barely left of 2 has a value that is exactly the same, or infinitely close, to the y-coordinate precisely at x equal 2.
Oh, so if it was just continuous, there could still be a corner.
Yes, because on a corner, the
You
3
still-
points are still really close to each
Yeah.
other.
Okay.
The 3 points are still really close. That doesn't mean the slope is the same on either side. Does that make sense?
Mhm.
It's very good. So this is checking, and again, it's very logical. It goes back to the fundamentals. We're using the equations for finding the points to verify that indeed the points are infinitely close.
So if it was saying if f is continuous, then we couldn't do this problem?
Correct. If all we knew was that f was continuous,
But if they said like if f is continuous and has a corner at here, but no other, like no other non-differentiable places or something?
the only other thing would cause it to be non-vertical tangent.
But like if they specifically said like it's continuous and its only corner is here, well like if it's
So Matthew has a loud sneeze, we've established that, so it's all good.
So if
No worries.
if f is continuous at x equals 2, but there was a corner at like x equals 10 or something, then we could do the same thing because it would be at a completely different spot that we could
Oh yeah,
disregard.
it's totally different places.
Okay.
Yeah.
So then we could do it, right?
We'd have to really design a problem that
But-
your thinking is the right kind of thinking.
But like you could do the limit of
Oh, as long as you know the
f
function is differentiable, then these two have to be the same.
like if it's differentiable at every point except for one that doesn't matter.
Then it will work everywhere else.
Okay.
Yeah. The definition is for that one point. So if it's differentiable somewhere else, then yeah, you could do it somewhere else. So
Okay.
yeah, so you find this, and then you
It makes sense.
come back here and say, oh, now knowing that the value of c is 2, I can plug that value of c into here and find the value of d.
So then it would be -2.
Right, because c plus d would be -2. So
Okay.
good work, guys. Good work.
Can we ask one more question
Please.
about 50?